These notes are about how to factor certain expressions. We're going to do a few examples and talk about some similarities and differences between each kind that we see. First, we see here that we have two examples. Factor 7x plus 14. First of all, what does it mean to factor? Factor means that we're going to write as a product. So right now, 7x plus 14, that's written as the sum of two things, 7x and 14. It's a sum. That means that we were adding two things together. A product means that we're multiplying. So how do we turn this sum into something times something else? One method, when you look at an expression that looks like this, we can look for something that, a factor that these two terms have in common. 7x and 14 both have 7 as a factor. So we can pull a 7 out front from this expression. I'm opening parentheses here because we're going to multiply that 7 by the quantity x plus 2. You can think of this as undistributing. When you learned about the distributive property, you would have gone the other direction, multiply 7 times x and then add it to 7 times 2. We're going the other way. We've turned a sum into a product, 7 times this quantity, x plus 2. We call that factoring out the greatest common factor, 7. Look at both of those. That's all we can do there. Let's take a look at this bottom example. 6a squared minus 2a plus 12a cubed. We're trying to look for the greatest common factor. I sometimes call that the GCF, greatest common factor. We want to look at the numbers as well as the letters. Let's look at the numbers first. 6, 2, and 12 are our coefficients. Can you see the factor that they all have in common? It's 2. They're all multiples of 2. Let's look at the a's. We have an a squared, an a, and an a cubed. A is in all of them. In fact, the highest power of a that's in all of them is just a power of 1. We have a and then a times a in our first term, a times a times a in our last term. So if I'm thinking about what's the most I can pull out front, I can really only pull out the a. Turns out our greatest common factor was a 2a. We're going to undistribute that, or see what we're left with in the parentheses. 2a times what is 6a squared? Well, 2 times 3 is the 6. A times a gives us the a squared. 2a times what gives us negative 2a? That would just be a negative 1. 2a times what gives us the positive 12a cubed at the end? Well, 2 times a positive 6 would give us the 12. A times an a squared would give us the a cubed. We factored it. We've written our original sum as a product. 2a times the quantity 3a minus 1 plus 6a squared. I'm going to leave it like that for now. Both examples on this page were examples where we could factor out a GCF. It's the first thing you want to look for when you're factoring something. Let's switch gears a little bit. Here, let's multiply these two binomials, x minus 3 and x plus 5. You should remember how to multiply two binomials. We just have to really double distribute. We have to multiply this x with both of these terms and multiply the negative 3 with both of these terms. We can combine like terms in the middle. A 5x minus a 3x gives us positive 2x. So the directions just said to multiply, and we did. We got a quadratic trinomial. I know it's quadratic because I can see that x squared term in there. And trinomial means quadratic. Trinomial means that there are 3 terms. X squared, 2x, and 15 are our 3 terms. Well, we multiplied two binomials and got this quadratic trinomial. Take a look at the next problem. It says factor x squared plus 2x minus 15. That looks familiar. That's what we just got up there. Remember, factoring is kind of unmultiplying. We're sort of trying to rewrite our expression as the product of two things. Well, we know what that's going to be. It's going to be x minus 3 times x plus 5 because we just did that example in reverse. But let's think about where it came from. The minus 3, you can actually see over there, and the plus 5, we can see back from our first step in multiplying. Notice the 2 came from the 5 plus a minus 3. The 15, or the negative 15, I should say, came from the 5 times the negative 3. It's coming directly from how we arrived at that quadratic trinomial. So to go backwards, we could think, what are the two numbers that multiply to this last term and that add to this middle term? And those two numbers are 5 and negative 3. So when we factor, we can write it as x plus 5 times x minus 3. Here I knew that the numbers were 5 and negative 3, but it'll take some thinking about it if the numbers aren't right there. Like this one. It has a very similar form. It's a quadratic trinomial. There's no greatest common factor here. And there's something else that's special about this. Notice our coefficient of x squared is 1. We would call this a Monic Quadratic. What that means is the coefficient of x squared is 1. And that's a good vocab word to know because we're really only focusing in this video on monic quadratics where that a value is 1. From what we saw in the last example, we know that we're looking for two numbers that multiply to negative 28 and add to negative 12. Multiply to negative 28 and add to negative 12. Can you find those two numbers? Well, they're negative 14 and positive 2. Sometimes it takes some thinking about, but if you're really good at mental math, this might come quickly to you. Otherwise, you might just have to play around with it to find those two numbers. That means that when we factor this, we can write our two factors as x minus 14 times x plus 2. If you wanted to check this, you could multiply out everything and see that you do indeed get x squared minus 12x minus 28. Let's look at this one. This one might be kind of special. Same game here. It's monic because our lead coefficient is 1. Two numbers that multiply to 49 and add to 14 are 7 and 7. Well, that's kind of nice that they're the same number. When I factor this, I can write it as x plus 7 times x plus 7. A shorter way of writing this is just x plus 7 squared. All that squared means is that we multiply that factor by itself. Notice that this quadratic was special because it was a perfect square trinomial. The way you can look for perfect square trinomials is if that last term is a perfect square, number times itself, and this middle term, that coefficient, is twice the number that you squared to get that last number. A perfect square trinomial is just that trinomial where those two numbers were the same that we found. So it ends up just being some quantity squared, x plus 7 squared. Take a look at this. X squared plus 2 triangle x plus triangle squared. This is just a general form of a perfect square trinomial. I know that I can multiply triangle times triangle to get triangle squared. Triangle plus triangle would give us 2 times triangle. So if we were factoring this, it would just be x plus triangle times x plus triangle. Just trying to generalize this. So now if triangle was a 5 or a 7, whatever, we now have a method to factor this. I could also call this x plus triangle squared. So that's another thing to look for, are perfect square trinomials. What if we multiply this out? Let's see, just like our method that we did before. We want to distribute each term to every other term. We get x squared minus 3x plus 3x minus 9. Negative 3x plus 3x That's just 0. So our final multiplication is x squared minus 9. Notice the middle terms canceled out. The middle terms are gone. You can guess what I'm going to ask for next. If you were to factor x squared minus 9, well, that's just going backwards. We can see here that that would be x plus 3, x minus 3. You can think of that as two numbers that multiply to 9 and add to 0. Since x squared minus 9 is just x squared plus 0x minus 9. It's the same thing as we did before. It's just not a trinomial. So these are the fun kind to factor. If there's no middle term and the x squared and the last term are perfect squares, then we can factor it pretty easily. Take a look at this one, x squared minus 64. Well, I know that the middle terms would have to go away, and I know that the last terms would have to multiply to negative 64. That's going to be x plus 8, x minus 8. Notice the structure of this factorization. The terms look the same, it's just the sign in between is opposite. These are known as differences of squares. This is a difference of squares. Difference means that we've subtracted. Squares mean that what we subtracted were two perfect squares. X squared is, of course, x times x. 64 is 8 times 8. The bottom one is also a difference of squares. It might be a little bit harder to see. 16x squared, that's actually 4x times 4x. So that is a perfect square. 25 is 5 times 5. So when I factor this, if I match the structure up above it, we know that that would be 4x plus 5, 4x minus 5. If you don't believe me, you can multiply that out and see that the middle terms do cancel out, and we are left with 16x squared minus 25. Differences of squares are common. You'll run into them sometimes. So it's very important to be able to recognize them. Notice, oh, those are two squares. They're being subtracted. We can factor them. Here's the structure. A squared minus 1, difference of squares. What's the square root of 1? It's just 1. Two numbers that multiply to 1 are just 1 and 1. So that's what that would look like. How about a squared plus 1? Two numbers that multiply to 1 but add to 0. If you're in the real number system, I don't think you can do this. So that's why it's really important that we notice that word difference of squares. Those will always be factorable. Just to summarize, the types of expressions that we've talked about, how to factor, include expressions where we can factor out a GCF, or a greatest common factor. We talked about how to factor monic quadratic trinomials. We talked about how to factor perfect square trinomials. Actually, we stuck with monic perfect square trinomials as well. And we talked about how to factor difference of squares. So these are just some things to look for when you're factoring, because we have really nice methods for each of these types. Are these the only things you'll be asked to factor? No. So stay tuned for more videos about more complicated expressions that you will be asked to factor. Good luck!